Oh, the mic was off. All right. So, it's 10 o'clock here in Moscow, and it's time to start. Thank you everyone for joining me. Please, if you hear me, if you see me, send me some kind of a smile. Maybe, I don't know, a heart. All right. All right. Awesome. Thank you very much. So now we can start. So, life is beautiful and amazing. My name is Vladimir Krichevsky. I'm from Sofoil. I'm a reservoir engineer, and I'm also a guest lecturer in Nafta College. So I welcome you all to our online live webinar, where we will talk about reservoir compartmentalization and cross-well connectivity. So here is how it's going to work. I'm just going to show you some slides. I'm going to talk a lot, probably. And then I will go back to this chat. I will see all your questions, and then we will try to communicate. I will answer you all. Or maybe if we don't have enough time, we will take some of your questions and move them to our forum. And there I will reply to you offline, and we can, keep on communicating offline after the webinar. All right, so I think you've seen enough of me. So again, that's me, Vladimir, self-isolating just outside Moscow. And I think that I will just eliminate my face. Right. And now let's move on. So, understanding reservoir compartmentalization and connectivity through long and short-term pressure and production data. So, for those of you who doesn't know about Sofoil at all, so we are a reservoir-oriented company. We provide a whole lot of services focused on the reservoir. So it's reservoir modeling, all types of surveys, well testing, production analysis, and a whole lot more. So what we're doing is we're trying to support the planning, the surveillance, and the control of reservoir development. Now, so we have some technologies of our own, which we are basing on when we're trying to recommend something to our clients. So I think that I will spend 1 or 2 minutes to explain each of these technologies. Actually, I will just explain 2 of them now, okay? So before I will show you the first case, I want to introduce you to this technology called MULTIWELL retrospective testing. So I will try not to talk too much, but the idea is to use the long-term pressure data as if you had, I don't know, a PDG or ESP gauge, and now you have a several years long history of the bottom hole pressure and of course the rate of your well. Then of course you will notice that starting from the very early time of life of your well will feel the offset wells. Because our well is never alone, so we have some offset wells which could be another producer or an injector. And as we start to produce from the well nearby, the pressure in our well, our focus well, will go down. As we start to inject, it will go up. So during all the life of our well, it is being influenced by the rate of offset wells, whether it's a producer or an injector. So the idea of this technology is to identify the influence of each surrounding well and simultaneously to see how the well itself would behave if there were no offset wells at all. So this is the point. So we are trying to decompose the well behavior into, well, let's say its own behavior and the impact of offset wells. So we do it by building a mathematical model basing on so-called unit transient responses. So every transient response is a mathematical function representing the pressure behavior in a well when another well is being launched with a unit rate. So transient response could be a drawdown transient response, which is a response in the well itself. So which pressure will I have if I produce in my well with just 1 barrel per day. And another class of transient responses are cross-well transient responses. So what pressure response will I have in the offset well if in my well I will start to produce again with 1 barrel per day? Right. So this set of mathematical functions will give me a model of a whole block of interfering wells. So when I have this model, I can reconstruct the history of formation pressure and then productivity index. And of course, I can decompose the pressure impact and see which well is draining the pressure out of me and which is in opposite giving the pressure to the area of my well. All right, but enough with the words. Let's go to some case. So case number 1, very fine fault and cross-well connectivity. So here we are with 5 producing wells. One of them is horizontal. No, 2 of them are horizontal, sorry. All of them are producers, and there is a probable fault just between this group of the wells. You can see it in dotted line, right? So we have the PDG history on the producer OP1. So let's see what data we have. Here's the bottom hole pressure in blue in the panel above. And you can see several panels of rates. So these are the rates and GOR of these 5 wells. So this is in fact all the data that we need inside MRT to build this mathematical model of this interfering block. So let's go to the results. So I don't want to go deep into the procedure because I think it would be, a topic for completely another webinar. But now let's just, look through the cases and see what we can actually get from this technology. So first of all, we reconstructed the formation pressure history for this oil producer number 1. Yeah, you can see that the pressure has been declining. Of course, it's declining because it's naturally depleted reservoir. And we can see also the history of a pressure drawdown. You see it was high in the beginning, and then lately it's been decreasing along with the rates, right? Okay. Also, we can build some prediction of formation pressure, and we can see that if we keep the current rates of all these 5 wells, we will see additional, slight additional decline in nearest month, right? Another thing we can deliver is the productivity index, because now, as we can reconstruct the whole history of formation pressure, and we also have the BHP, and we also have the rate, we can just calculate the productivity index, and I plotted here in yellow points in the top panel, and you can see that the productivity index has been relatively stable. Well, there's no issue with the well. We don't see that the contact is getting any worse, so it's actually fine. Another thing we can deliver is IPR. So now, as we have the whole history of formation pressure, we can build several IPR curves for any given formation pressure. And we can build a model, for example, a Vogel model right here, to fit all this data that we see. And then we can actually try to predict what would be our IPR later on as we deplete the reservoir even more. Right? So on this plot you can see the theoretical Vogel curves, which we tried to fit on these colored points, which are in fact rates with the different formation pressures. Right. Now, another thing that we can give is the estimation of reservoir and well properties. Because as we get this drawdown transient response, we can plot it on a log-log plot. These are two black dotted lines here, and they will represent the model of the well and reservoir. So now I just compare it to these colored dots, which are one of the build-ups in the history of this well. So now you can see that somewhere around radial flow, the MRT response actually fits the PBU, but we have the long and smooth history, and we can build a sufficient model given the precise estimation of reservoir properties, reservoir geometry, and we can of course quantify it with the numbers here. All right, and the same thing we can do with the cross-well transient responses. So what is a cross-well transient response? Again, if we produce in well number 1, what would be the pressure response in well number 2, right? So this is actually a kind of a very simple pressure interference test. So I can just interpret this data, for example, like here on this log-log plot. I can plot it on the log-log plot, see the radial flow, and then estimate the transmissibility. And that would be the cross-well transmissibility in average. And then another thing we can get is the decomposition of the pressure impact. So our well is no doubt under impact of surrounding wells, but now we can just quantify the impact of every well. So what we can see on this plot is that we see the impact of producers number 2 and 3, but we don't see any impact from producers number 4 and 5. So if we go back on the map, you will see that these two wells behind this fault, because of insufficient history of these wells, and what I mean here is in order for this technology to work, every well needs to have some history of events in the rate sequence. So if your well has been producing stable ever since it's been launched, it would be very hard to say if it's impacting another well or not, right? Because the pressure would just smoothly fall down, and you know, it could be due to reservoir boundaries, or it could be the impact of these wells. And there is no technology in the world which could actually say which is which, right? But in this case, both of these wells, they have very sharp events in the history, and as we don't see any impact, we are quite certain to say that this fault is impermeable after all. So that's the story. And additionally, there is another finding. So we estimated the transmissibility around the well itself, and then we estimated the cross-well transmissibilities between these two wells and these two wells. And you can see that the values are quite close. So it seems like the reservoir is quite nice, and the sweep, aerial sweep, vertical sweep here is actually quite nice. So maybe these reservoirs could be considered a nice target for a water flood. But again, now that we are certain that we have this impermeable fault here, then the strategy of the water flood would, of course, be changing, right? Because we cannot create a sufficient water flood system here with just one injection well, unfortunately. Alright, so before we jump to another case, I need to introduce you to another technology, which is the kind of pressure interference testing. So the technology I'm talking about is called pulse code testing, PCT, and we are using this technology to estimate the precise connectivity between wells. So this technology is, again, it is more precise than the MRT, because we are focused on some wells, and we intentionally create the history of rate changes, and we do it in a very short amount of time, like, I don't know, a month, 2 months, and we are sure that the properties that we are trying to assess are not changing through this time, right? So the idea is quite old. I think the idea of pulse testing has been developed in the 1950s and has been widely used ever since, across the world actually. And the idea is to create a pressure disturbance in one well, which you call a generator, and to set the gauges, the pressure gauges, in offset wells, which we call pressure receivers, and try to see the response of these receivers to the signal which we send in generators. So that's quite simple. So when you create a pressure disturbance in one well, so how can you do it? You will just change the rate. It could be either an injector or a producer. You can just, shut it and then produce, then again shut and then again produce, or inject, right? So then this pressure disturbance would propagate through the reservoir, and then at some point it will reach the receiving well. And when it reaches the receiving well, it will have a wavy shape, let's say, right? It will be like a sinus, okay? And there will be some kind of a time gap between the maximums and minimums of this wave and the times of starting injecting or shutting in the generating well. And this time gap strongly depends on the distance, of course, and the pressure diffusivity, which in its turn depends on permeability and current reservoir saturation, right? And another thing is that this pressure disturbance would have some large amplitude in the generating well, and when it comes to the receiving well, the amplitude would be, of course, substantially lower, and this decay of amplitude, right, as the pressure travels through the reservoir, depends on reservoir transmissibility. So reservoir transmissibility also depends on permeability and saturation, of course, but it also depends on the connected thickness between the wells. So now you can see that with any kind of pressure interference test, we can get two numbers independently: the transmissibility and pressure diffusivity. And in various cases, we can use this information to derive something really important, like, I don't know, permeability, or an average saturation between the wells, or the connected thickness between them, right? Okay, so now let's go to the case. You can see more in this SPE paper, by the way. So we are trying to justify an infill well, which has been planned by one of our clients. So what we see is the offshore field under water flood, many years under water flood, actually. So we have some producers here in the crestal area, and we have some injectors here close to the oil-water contact. Actually, this pulse code testing which has been performed on this field is a part of a large survey campaign, including production logging and modeling and so on and so on. So I'm just showing you a part of it. So if you want to know more, just please refer to the SPE paper. But there were some issues here regarding well integrity and reservoir continuity. That's what we are going to talk about. So we had two PCT cells here. Cell number 1 here in the aquifer zone, and cell number 1 only used injection wells. So we had this well number 1, the generator, And these wells, number 3 and 4, were used like as receiving wells, right? And here on the right, you can see the scheme of the cell number 2. So we used an additional generator here, well injector number 2. And these 3 producers were used as receiving wells here, right? Okay. So these are raw results of the pulse code testing, transmissibilities, diffusivities, but in terms of the results and recommendations, here is what we actually seen. Well, here in the west of the reservoir, we see that this fault is in fact impermeable. This is a limited extension fault here, and we can see it with the diffusivity on this interval between well number 1 and well number 4. So if the pressure were to travel along the straight line here, the diffusivity would be substantially higher. So we can actually see that the pressure has to travel around this fault here. So we can confirm that there is an impermeable fault here, and we can also confirm that there is still communication between these 2 wells, right? Another thing that we see, again with the diffusivity and transmissibility, is that there is a baffle, some kind of a baffle here, which prevents the pressure from propagating between these 2 wells, or these 2 wells. So another thing that we can see is that there is a high permeable channel between these 2 wells, well injector number 2 and producer number 3. So now, as we know a bit more about our reservoir, we can see that the idea of placing an additional producer in this zone is actually quite nice, because we don't have that much injection here, because some part of injection in these 2 wells is actually cut from this area by this impermeable fault. And there is still a baffle here which also prevents the water from this well, for example, from coming to this southern part of the reservoir. So there is probably a bypassed oil zone here. So we confirmed that it is a nice place for an infill well. And as a result of this campaign, actually, I think a lot of activities have been made on this field, and one of them was this drilling of this new infill well. This idle producer has been converted to injection, and a new producer has been placed here in this target zone, and as you can see that the initial well test is pretty nice. So we had a 0 water well with a very high oil rate here. Okay. Another case, I call it all weapons to verify the fault. So one of our clients is developing a large field. The reservoir is carbonate, by the way, and they have a whole lot of faults which they see on seismic maps, but they are not confident about whether these faults are transparent or sealing. So the point is to understand if this particular fault going across the field is splitting it into compartments or not. So our client has 2 wells, one on each side of the fault, well number 22 and well number 20. And they have a whole history of downhole pressure for both of these wells, and they want us to reconfirm if this fault is sealing or not. So first of all, we will try to analyze the pressure and rate history. You see that we have the whole history of well number 22 and well number 20, and also we have history of several surrounding wells. Some of them are injectors, some of them are producers. Well number 22 has been producing for I think about 2 years now, and well number 20, well, about 1 year, right? Okay, so first of all, we will try to use the history of the well that has been producing the longest, well number 22. Let's see this history. I just want to give you a snapshot of the pre-processing of data for MRT technology. So first of all, we have a lot of build-ups for the history of well number 22. And if we will just plot this build-up on the same log-log plot, we will see that the radial flow and the apparent transmissibility is decreasing through time, right? As a matter of fact, this only happens in the near wellbore zone. So unfortunately, during the production here, we have crossed the line of bubble point, and now as our pressure is falling below the bubble point, we have more and more gas liberating in the near wellbore zone, which creates a two-phase flow in the zone, and the transmissibility is going lower and lower and lower. So this is actually not good. So unfortunately, the water flood here is not as efficient as our clients wanted it to be, right? This is point number one. And point number two, as at some point in time, we can see that all our pressure buildups are being distorted by the gas humping. So what we can actually see is that initially we have a normal buildup behavior, because there is a whole lot of liquids. We have a full liquid column below the gauge, right? And then as more and more gas is coming into the well, it presses the liquid level down and down, and then it goes below the gauge, and we can see that unfortunately, yeah, our pressure rises and rises, and then it stabilizes, and now we can say that there is a full column of gas below our gauge. So of course, if we need to perform any kind of analysis of this data, we will need to filter out this part of the pressure buildup. All right, now to the results. So what we can see here is, unfortunately, none of the offset wells, well number 20, including well number 20, is showing any pressure impact onto well 22. So we see quite stable reservoir boundaries. They could be either static or dynamic, but we just cannot see any well interfering particularly with this well number 22. So it again could be due to insufficient history of rate changes in some wells, because you can see that I didn't put all the wells, all surrounding wells here, because some of the wells unfortunately had very stable rates. So maybe they are still impacting this well, but out of these three wells, we can see that we do not see any impact. So this is like a first sign that wells number 20 and 22 are not interfering. Well, also, of course, we identified the reservoir and well properties. We estimated drainage area, the reserves for this particular well, and so on and so on. Right. So, but now let's take a closer look. So we can see that after the well 20 has been brought online and started producing, there was a small, well, I say a slight additional pressure decline in well number 22. And if we put all the history into our software, we can see that it is not an impact of the well. But what if it is? So let's just build a small model, and this model would say that, okay, let's take this additional pressure decline and say that it is an impact of this production. And then, based on this model, we can predict the pressure behavior of well number 22 with the impact of well number 20. And here is what we would see. So we have this long pressure buildup here, and during this buildup we have a small buildup here on well number 20. So we can see that if really this well would impact our wells so much, then on this buildup we would have this additional hump, and it would be quite recognizable because it would be like 1 or 2 bar amplitude. So that's quite a lot, and we don't see it, so probably it's not the case. Another thing is we had a very long build up here, like a month long build up here, and we were supposed to see a very high pressure response on well number 22, which we don't. So again, this additional pressure decline has nothing to do with the production of well number 20, and most probably it is caused by the increase of gas production in this well. And actually, we can trace through history of this well, we can trace that several times when GOR goes up, the BHP goes down. All right, and then the last weapon to ensure if there is or there is no fault here is the pressure pulse testing. So our client themselves, they performed the pressure pulse testing in order to understand the connectivity between these two wells. So they didn't get any results, and actually we love this kind of testing because we specialize in this type of testing, and we just took the raw data and reinterpreted it with our mathematical tools. And we can see that there is no response in the well number 20 on the signal in well number 22. So we have this, let's say, trust coefficient, which show the correlation between the signal and the impact, and we can see that the trust coefficient is actually below 0. So the response is totally 0, so negative. No, these wells are not connected. Well, to be honest, I need to say that technologically this test was not perfectly fine. We can see that there is some kind of a pressure disturbance on well number 20, which was a receiving well. You can see this periodic, well, humps in pressure, which in our practice seem to be caused, most probably caused by the hydrates or maybe some paraffins which are depositing on in some place, and then they are washed with the flow in the well, and then the pressure goes down again. So this is like a periodical process, and this, of course, this affects the robustness of any pressure interference test, unfortunately. But again, summing up all our findings, we can say with the high confidence that these two wells are actually not connected through the reservoir, and there is, after all, a sealing fault between them. And well, actually, again, this investigation was not about just these two wells, but I can just tell you that we also found that there is another fault here, which you don't see on the map, by the way. Another fault right here between these two wells, E4 and E22, going in the same direction, and it actually affects the whole strategy of water flood. So as a matter of fact, this well number 22 is sitting in the compartment which is not yet water flooded at all. So we don't see any injector in this compartment. So probably there is a need to convert another producer or to drill another dedicated injector into this compartment specifically. All right, now let's go to case number 4. Justifying well spacing. So here we are in a big oil field, giant amount of reserves actually, and it's all been drilled with horizontal wells. This is only a small part of the field actually. Yeah, by the way, this is an SPE paper. You can see more of this in this SPE paper. And the regulator, the government regulator, is asking the oil company, are you sure that your well spacing is close enough? Are you sure you do not need to drill infills now? And one of the means to understand the how close for now is the well spacing is to understand the cross-well interference. So we had several wells here with the long bottom hole pressure history, which we used as focus wells for MRT. So let's see the results. So after we performed the MRT, we had two histories of formation pressure around each well. You can see that this particular well, number 6, has the deepest pressure decline and the highest depletion. As a matter of fact, it has the lowest transmissibility in this area, so probably it's just a local thing. But again, it seems like all these wells are connected, and they are connected to the offset wells, and we see some pressure interference. But for now, as we don't have yet any water flood, any water injection, our prediction of formation pressure is a further decline, of course, right? And then here on these 4 plots, you can see the cross-well impact. So the colored lines on all of each of this plot are showing the individual pressure impact of wells surrounding these focus wells. And what we can derive from these plots is that the cumulative impact of offset wells for almost each of these wells is actually higher than the impact of the well itself. So most of the depletion now is caused by offset wells. So qualitatively, it tells us that the well spacing is quite sufficient, because we have a serious decline in the wells due to offset wells production. Also, along with these results, we try to identify the wells which would be nice for converting to injection, because the client is actually considering emerging the water flood in this field, and we can see that some wells have quite high pressure impact, and sometimes it's caused by low connected thickness between the wells. So each of these wells would not be such a good candidate for conversion, because it would be quite soon flooding the other well, and we would have the early water breakthrough in this pair of the wells, right? Also, we would see some wells with a very low pressure impact, and sometimes it would mean some kind of a baffle between the wells. And again, in this direction, the water flood would not go as efficiently, right? But we can still see a couple of wells on this field which we think are nice candidates for to be converted to injection. One of them is right here in the center, and another one, let me see. Yeah, as a matter of fact, here is another one. So these two wells, this well outside the area and this well right in this middle of it, are nice candidates for converting into injectors. So this is another type of recommendation that we can get from just analyzing the history of bottom hole pressure and rates on the well. And another thing we saw here is that there was a drop in the productivity index for each of those wells. So as our reservoir pressure is going down, and it again crossed the line of bubble points, unfortunately we have more and more gas around the well in the reservoir, and unfortunately it leads to decline in productivity index. And for some wells the decline is quite sharp. You can see that for well 4, for example, the productivity index is twice less than the initial one. I think this is it. So I tried to give you a glance at our technologies and showed you several field cases. So now Again, if you have any questions, I just welcome you to our chat, and let's talk, let's communicate. Thank you very much for your attention. Thank you very much, everyone who has been joining us from across the world, actually. Right. Wow, I had a lot of smiles initially. Thank you very much. Will this be uploaded later? Yes, it will, of course, and you will all be provided with the link. Of course. How do you translate transmissibility and diffusivity to reservoir properties? That's a very nice question. So, as a matter of fact, transmissibility is Kh over mu, right? And the diffusivity is K over mu and the connected thickness. So we have two numbers and we have three variables. Doesn't work like that, right? So what we need to do is we need to eliminate one of the variables. There are several ways to do it. Sometimes we can just rely on some historical data on permeability, for example. Additional PCT tests in the areas where we know the saturation for sure. Well, for example, like in this case which I showed you in the beginning, we had 3 injection wells very close to oil-water contact, and we might be quite certain that the saturation between these wells is critical water saturation, right? So, I mean residual oil saturation. So now we can be quite certain that we have 2 numbers and 2 variables, and we now can understand the permeability and connected thickness, for example, right? Okay. If reservoir between wells is not homogeneous, then what transmissibility and diffusivity would mean? That is a very nice question as well. Of course, the heterogeneity of the reservoir and of course the boundaries of the reservoir would affect the properties. And if we see the difference of the parameters that we get from what would we expect from, I don't know, an open hole logs and the simulated PCTs which we can run through the model, then we would of course need a numerical model to interpret the results. So as I'm trying to show in the latest case, we would need to build a 2D numerical model, and then maybe if it's not sufficient enough, we would need to switch to 3D model in order to understand what it really means. I mean, our result. Yes, that's true. Diffusivity, as a matter of fact, in Russian is пьезопроводность. Okay. What kind of results can be expected in a well with multiple commingled zones? Yes, that is a very nice question as well. Of course, if we have a commingled reservoir, then and if all the wells are perforated with the same set of reservoirs, then we would just get an average estimate of transmissibility and diffusivity. That's very true. Sometimes have a receiver dedicated to an individual layer, then we would have the properties of this layer individually, right? Yeah, but it's not always the case. So in every case, we need to see what we actually can deliver. MRT helping calculate the remaining reserves. Of course, there are such cases. For example, this case with the fault in a carbonate reservoir, we estimated the remaining reserves for this well number 22, and we saw a compartment which is big enough to drill an additional injection well, and we had a lot of reserves in this compartment. Yes, in almost most cases we can help understand the number of drained reserves. That's true. MRT for gas fields. Thank you very much. Well, I hope doesn't have any strict restrictions. I'm sorry. to work with the gas data. So I think we will soon be able to show you something. And of course we will publish it, and it will go to SP instantly. How far the distance of well to be interfered from any surrounding well? How far the distance? Well, this has to be pre-designed, of course. So when we plan any pressure interference test, we need to pre-design it. So we need to see what would be the amplitude of the pressure disturbance which we can create with the generating well, and then we need to model how big would be the response on the receiving well, and do we have a pressure gauge in this well which can help us register this pressure impact. So this is the matter of the pre-design, and I can't tell you like some uniform number, because it's not like that. But for low permeable reservoirs, sandstones in, for example, North Russia, 3 millidarcies and below, the distance would be, I think, about 5 millidarcies, and the distance about 800 meters. The test would take about 10-12 days. This is what I remember, and of course it doesn't only depend on permeability and the distance. We need to take viscosity into consideration, but I mean, in average, these would be the numbers. Okay. Right, a lot of question about commingled wells. That is true. Producing multiple reservoirs are producing from the same well with single PDG. Well, of course, we can't expect a miracle from any kind of technology, right? So if you have only one pressure gauge in the well, then you will only get one number. So unless you have the dedicated PDG and a dedicated string for any reservoir in your well, you will just get an average estimate, unfortunately. So in order to eliminate the uncertainty which we have in these results, we would have to run, for example, a production logging, a cased hole logging, to understand how individual layers are producing or injecting. Okay. How the PCT could help to enhance the dynamic modeling? Well, there are a lot of ways to use either MRT or PCT results in dynamic model. So I think the first one would be just to calibrate the model with the formation pressure which we can provide with MRT technology. Then for example, for PCT, in any model you can run a synthetic PCT and try to see if the transmissibility and diffusivity that you get in the model is corresponding in what you get in the real life as a result of the actual field test. And if you see the inconsistency, then or systematic inconsistency, then it's time to see the way how you can improve your model to better fit the actual results. Also, you can calibrate it to productivity indexes of the well, and you can, if you run for example, a PCT, you can see the connected thickness between the wells. You can then see your conformance profile between the wells in the model and try to calibrate it according to the findings which you get from PCT. So there are actually a lot of ways, and I think we could run an additional webinar just to show you how the dynamic model could be calibrated to the dynamic test results. Okay. Any limitation on the length of the horizontal? No, actually not. So there is no limitation on any type of well design. It could be a horizontal, it could be a fractured well, it could be a fracked horizontal. That doesn't actually matter. So both technologies would work with the wells with any type of completions. In terms of the risk in connected, what are the benefit of MRT compared to running multi-well rate transient analysis? So, well, you see, the rate transient analysis well, it's like a forward technique. When it comes, well, I'll tell you what I mean. When it comes to analysis of several interfering wells, what you can do in RTA, if you can perform the analysis with a single well, then you can see that your model doesn't actually fit, and you see the impact of some surrounding wells. Then you can just add them to the model, either analytically or numerically, and then you will try to fit the pressure and rate data, adding other wells. Forward tasks. So you would model, you would see, okay, this doesn't fit. Let me, I don't know, work with permeability in this area. Okay. Okay, now this well is okay. I see the impact of this well I can fit in my model. Let's move to another well. Okay, it doesn't fit. Let me change the, I don't know, thickness field around here. Okay, now this well fits perfectly, but the first well, again, it doesn't fit again, right? And then you will just go round and round in circles. So before the multiple well deconvolution, as a reservoir engineer, I used this routine, I used this workflow as well, and it appeared to be very time-consuming, and it was very, very, well, subjective. I mean, we had two reservoir engineers that were given the same block of wells, and they needed to fit the well behavior considering the impact of surrounding wells, and they were both pretty capable of fitting the pressure all right, but the model looked absolutely different. So they had two absolutely different models at the output. So I think that the multiple well deconvolution, which sits inside the MRT technology, is in fact the right tool, because we have this very hard task for the reservoir simulation. We transfer it into mathematical field, then we decompose it with mathematical tools, and then as we return this simple mathematical task back into the reservoir, we can have very simple tasks like I have the unit rate production in this well, and I have the pressure impact in this well. Can I estimate the cross-reservoir parameters? Of course I can. It's quite simple. So I think that the advance of MRT technology is, well, quite huge here, and it would be a more robust result for you, and it would help you understand the dynamic drainage volume and the static drainage volume. So if there were no offset wells around your focus well, what would be the drainage volume then? Well, which is also a very useful finding. All right. How can we contact you for further discussion? So there is a forum on the Sofoil.com site, so I welcome you all there. So if you have any further questions, I would love to see them on the forum. So please register, send your questions, and we will just continue communicating offline. Okay, how do you design the PCT test? So in most cases, we just use the simple 2D model. It would be a numerical model. We would just take the part of the field. Let's call it PCT cell. We will build the map. We will build the boundaries, the probable faults that you see. We will put the expected permeabilities and thicknesses into the model, and then we will just try to model the PCT and see what would be the synthetic responses. And then we would see how long should be the test in order for us to get the recognizable responses on the receiving wells. So that's how we pre-design it. How independent is MRT results in the connectivity study? Would fault be an input? Now, of course, it would not be an input. It would not be an input at all. So, of course, we just everything that goes, all that goes into the multiple well deconvolution procedure, which is inside MRT workflow, is the pressure and the rates, nothing else. So the procedure has no information about the distance, about the geometry, about the completion, about any type of faults at all. So that's how it works. So I would say it's pretty independent. Yeah. All right, guys. So I don't see any questions. I think it's time for us to say goodbye. Thank you very much again. Thank you very much, everyone, for joining around the world. And I hope you are all safe. I hope you are all staying at home. And I wish you all good luck. I wish you all a good week. And happy isolation weeks for every one of you who is self-isolating just like me. Life again is beautiful and amazing. And see you on the next webinar. Stay cool. Bye.